Okay.
Okay, great. So welcome everybody. So in this week's edition of the Motivic Geometry Seminar, I'm really pleased to introduce Adrien Dubouloz, who will explain to us stable A1-homotopy at infinity.
Okay. Thanks for the opportunity to talk in this seminar. I wish I could have been present this year in Oslo, but well, this wasn't possible for obvious reasons. I will report on joint work we did with Paul Arne and Frédéric Deglis on stable A1-homotopy type at infinity. My aim is not to enter technical details or explain the detail of important computational ideas that you have to bring to do something, but to give you rather some context and motivation for developing that kind of ideas. And I will start with topological consideration, just to remind you, if you don't know about this, from where these things are coming. Let me share my screen. My usual Blackboard handwriting is very bad, and my online handwriting is even worse, so I apologize for this. So let's start with some good old topology viewpoint. Topology. It starts very bad. Topology reminder. So let's say we consider reasonable topological manifold, reasonable topological manifold. So locally compact, separable, whatever you prefer, metric space, things like that. Maybe you want to assume that it has an exhaustion by compact subset, or else the homotopy type of a finite CW complex, whatever you need, so that the next thing I will say makes sense. So if you have a non-compact manifold, maybe you are interested in understanding the structure of M around infinity. And for this, you have a gadget which is called the N space of M. Which is just, you look at the set of proper maps continuous maps, which you undo with the compact open topology. And you call this the N space. So some obvious examples. If M is compact, then there is nothing to do with this. This is just the empty set, because every map will extend to a map to M defined at infinity, and then there is no proper map with this property when you restrict inside infinity. So if M is non-compact, then this N space has something, and not compact. Then it can happen that other M is not empty in general. And then you can speak about the homotopy type at infinity of M. At infinity of M, or it's just the homotopy type of the N space. Okay, so there is, just for it's good to remember that there is a natural map from the N space of M to M, which just associate to a map, to a proper map like this, the image of 0. So it's not totally unrelated to M. And then you can easily find some basic properties. Of Adrien. So the first one is close to intuition, that since E of M captures some behavior at infinity, if you remove from M some compact subset, this will not change the homotopy type at infinity of M. So if you have M prime inside M closed compact subset, then you get an induced map from the N space of M prime to the N space of M in an obvious way. And this turns out to be an homotopy equivalent. So, well, this immediately allows some computation. This remark immediately allows some computation of some simple homotopy types at infinity. Say, if you look at the Euclidean space, RD, then inside this RD, you can just remove some natural closed compact subset, which so it's just the complement of the open sphere of radius 1. And so this guy is just SD -1 cross 0 infinity. And so from this, you see that the N space of RD is the same, is homotopy equivalent to the N space of that. But if you look at the definition, what is the N space of that? If you take a ray going to infinity, then it meets the infinity at a point which is parameterized by a point of the sphere. So basically, what you get from this is that the N space of RD is the same as the N space of this guy, which is basically just SD -1. So, well, so the homotopy type at infinity of the Euclidean space is just a sphere of dimension 1 less, right? And you can generalize a bit this kind of observation more generally. If you start with M smooth compact, and inside this you take smooth closed smooth compact manifold, then you can try to think about what is the N space of M minus Z. And now if you look at an exhaustion of M minus Z by big co-compact subset, you will see that basically by excision, this thing is essentially the same as, say, a tubular, well, sorry, it's a tubular neighborhood of Z inside M, in which you remove Z itself. So since we're working with smooth manifold, this is the same as up to homotopy equivalent as the normal bundle to Z in M minus the 0 section. Right? And this you can just see as a nice manifold, because this is just, well, if you assume everything is metric, this is the unit sphere bundle in the inside of the normal bundle. viewed as a sphere bundle over Z. So you see that the homotopy type of this n space is just the homotopy type of the unit sphere bundle of the normal bundle to Z in M. Right? So for instance, let's take a very simple example of application of this. If you start with M is as smooth, complex, say algebraic for simplicity, algebraic surface. And you assume that Z is just a copy of complex projective line in it. So then the n space of S, well, smooth, complex, projective, if I want to have this absolute on the space. This is the unit sphere bundle, unit, then it's a circle bundle, unit circle bundle of the normal bundle of P1C inside S over P1C. But I look at this thing as being topological manifold. So P1C is just the sphere S2. This normal bundle as a complex bundle on the sphere is just some OP1 of D. And then the unit circle bundle of this, viewed as a real topological vector bundle of rank 2, is just a circle bundle with Euler class D. Right? So if I look at the sphere, at the unit sphere bundle of P1, this is just with this normal bundle, this is circle bundle on S2 with Euler class. D. Okay, far so good. Any question? Okay. So you can slightly generalize this more generally again. If you start with M compact, smooth manifold, smooth, and inside you take Z closed, and you assume that Z has a good tubular neighborhood in M. So this means that you can find just an open neighborhood of an open neighborhood U of Z in M such that Z is strong deformation retract. Oops. Deformation retract of U. Then by doing exactly the same game as we did before in the smooth situation, you find that the n space of M minus Z is this good tubular neighborhood of Z inside M. Well, sorry, the opposite. No, it was fine. In which you remove Z. So that's punctured tubular neighborhood. Then the problem, of course, is in comparison to the case where Z is smooth, there is no obvious way to get a handle on the structure of this tubular neighborhood. But still, just have to keep in mind that it could really apply, for instance, to So a pair of normal crossing curves, say that would be just the zero set of this map in the real setting. And then if you look at the set norm of f lower than epsilon, then this creates you some good tubular neighborhood of that guy, of that zero set. So in particular, if you work with complex algebraic variety and an SNC divisor in it, a smooth normal crossing divisor, it will always have a good topological tubular neighborhood in that sense. So in practice, you have a chance to describe the topological homotopy type at infinity of these complements. Okay, so why do we bother about homotopy types at infinity? So there is one sledgehammer reason, which is not the one we are interested in, but let me remind you this. There is the open version, open Poincaré conjecture, which is solved, by the way, but it says the following. If you look at an Euclidean space, RD, then it can be characterized among smooth manifold is the unique smooth manifold. Which is contractible. Okay, definitely it is contractible. It has to be, and what is called simply connected at infinity. So there is some homotopy type at infinity here, and if you have any smooth manifold M, such that, say, the M space of M is, say, path connected, in particular connected, then you can certainly define the pi1 at infinity of M just to be the pi1 of the M space. And in this formulation, it tells you that to detect an Euclidean space among smooth manifold, you just have to check whether it's contractible and simply connected at infinity, in the sense that this group is trivial. And well, you probably all have heard about the fact that this condition is really necessary. There are open three manifolds which are contractible and not simply connected at infinity, for instance, the famous weighted manifold. So, okay, that's it for the general topological context, but you know, let me tell you about homotopy, topological homotopy at infinity in algebraic geometry. So surprisingly, in some sense, it seems that the first who considered applications of these ideas to problem in algebraic geometry, in complex algebraic geometry, since we work with classical topology, is Mumford. And what he gave is a characterization of smooth points of normal complex surfaces, in topological terms. So I think it's a good idea to discuss this a bit more, because it shows you how homotopy at infinity pops up in a very unrelated context. So the question was raised by Mumford and other people was to characterize the smoothness of a point on a complex algebraic surface by the topology of the underlying analytic space in a neighborhood of a point. So you pick as a normal surface, as normal algebraic surface over C. So it has at most isolated singularity. S, you pick a close point. And you can look at the local fundamental group of the surface at this point, which for simplicity, if you work in the analytic topology, just the pi1 of the complement of the point S, where U is a small Euclidean analytic, if you wish, neighborhood of S. You can define it as a limit object where you take a filter of open neighborhood if you wish. So, and Mumford's result is that S is a smooth point. If and only if this local fundamental group is trivial. And well, to relate, well, the Mumford's proof is basically relating this local fundamental group to something which looks like the fundamental group of a punctured tubular neighborhood. And here is briefly the idea. Well, first you take log resolution. This is just a resolution of singularity, but with certain property, a log resolution of the pair SS or US, if you wish. So by this I mean this sigma. So sigma is a projective or proper birational map. With the following property, you want STL to be smooth. You want sigma -1 of S, which call the exceptional locus of sigma, to be an SNC divisor, an STL divisor. And if you restrict sigma to the complement, it should be an isomorphism. And now, if you look at the definition of this local fundamental group, you can try to pull back along this map to see that you can identify the local fundamental group to the pi1 of a tubular neighborhood of the exceptional locus in STL minus the exceptional locus. So in other words, you can just compute this or interpret this pi1 as being the fundamental group at infinity of the irreducible component of the n space of S, consisting of proper maps from 0 infinity to, well, let me write. Let's see. So P1S is interpreted as the pi1 infinity of the irreducible, the connected component of, so you look at the n space of S minus the point you're interested in, consisting of maps. So you go from 0 to 50 S minus S, but so S minus S by construction is the same as S tilde minus the exceptional locus, which extend to maps. The H bar from with H bar infinity. Okay, so that you just look at the component inside this consisting of maps which have an extension such that the image of the infinity goes to a point of the exceptional set. Okay, so this is just a reinterpretation, and the main point of Mumford argument is what is called plumbing construction. So if you look at this exceptional set, so it's a union of irreducible components which are just smooth curves, smooth algebraic curves, smooth compact algebraic curves. See, and well, we know that if we had only just one curve, we could compute if is just one EI, unique component, then we know by what we observed before that then P1S is just the pi1 of tubular neighborhood of EI in S tilde minus EI, but this is the same as the pi1 of the normal bundle of EY inside S tilde minus EY, minus the zero section. Okay, so if we have just one component, we already know how to compute this. And the problem is, how can we compute this tubular neighborhood in the case there are many components? So the Mumford plumbing construction provides you a way to describe the good tubular neighborhood of in S tilde minus E as a gluing, called a plumbing, gluing of good tubular neighborhoods of the EI. S tilde minus EI. So as we so before this tubular neighborhood are just in all case circle bundles over algebraic curves. So from this, what you get is a presentation of the pi1. In terms of what? The generators are made from generators of the pi1s of the components. The fibers of the circle bundles, fibers of the S1 bundles, and that's it. So that's all the relevant loops you can find in these building blocks, plus relations given by the gluing, by understanding the gluing. The gluing. So to summarize, the Mumford's plumbing construction is really one way to construct an object representing this tubular neighborhood, this good tubular neighborhood of an SNC divisor from good tubular neighborhood of each of the components. Okay, so maybe I say another word about the proof. What about the proof? More than the proof. What about the proof of the main theorem?
Can I ask a silly question?
Yes, sure.
So is it so easy to calculate the pi1 of the punctured normal bundle? I mean, if it's some extension of a z by the pi1 of the base.
Exactly. Yeah.
Then yeah.
Well, for the pi1 is complicated. You have to understand this extension in general. I mean, it can be a non-trivial extension. If you look just at diabilization, then what do you get is a split sequence, I guess, relating the homology of the total space and the homology of the base, and just a twist by the Euler class of the S1 bundle. But in general, no, that's complicated. And Mumford is not really explicitly doing this in the proof, and here is one of the reasons.
I just wanted to. I wasn't sure if it was easy. Okay, thanks.
In general, no. So the proof is so you assume that this pi1 is trivial. Well, the first thing you can extract is that this exceptional set where you took this log resolution is a tree of p1s. And this solves somehow the question about the extension in that case. The crux is that every time you have a loop coming from the base of one of the components, yes, every time one of the components has non-trivial pi1, you find some loop in this tubular neighborhood corresponding to a lift of a loop on the component. And so every component has to be a tree of pi1, otherwise not possible. And then you have to worry about the dual graph of this configuration of pi1, but you can imagine that, you can immediately imagine that if you have three pi1 intersecting like this, well, geometrically, you immediately some cycle here, some non-trivial loop. So, and that's what Mumford is arguing. So first, this implies that this is a tree of pi1. And then you have two things. You have a group theoretic argument. Which tells you that under this hypothesis, there exists a component, which is a P1 with normal bundle O P1 of -1 intersecting at most two other components. Good.
No, but that's under the assumption that the pi1 is trivial or something.
Yes.
Okay.
And the analysis is made using the presentation he gave, and if you have if you can't find this kind of thing, then there exists some branch somewhere, and you can just check by group theoretic consideration that the pi1 can be trivial. No, the proof goes like this. You have a pi1 with normal bundle O of -1, so you know you can contract this to a smooth point. And the fact that it intersects at most two other components tells you that after this contraction, the image of the exceptional set will still be an SNC divisor. So after this contraction, what you get is another log resolution, but with one less component in the exceptional set. So you keep doing this, and at the end, what you find is just that you have a log resolution consisting of an exceptional set, which is just a P1 with normal bundle O of -1. But this is exactly what you get by blowing up a smooth point. So that's the basic idea of Mumford's proof.
I seem to remember, maybe I'm confusing this with another paper, but there's some essential point of some intersection matrix being negative definite.
Oh yeah, it's absolutely crucial that the intersection matrix is negative definite in this part of the argument.
Oh, okay.
And the analog will come in a second. It is indeed crucial to conclude that it's a P1 with normal bundle O of -1. Otherwise, it could be 1. And that makes a big difference. And now, soon after Mumford, Ramanujam probably got inspired by this consideration, and he applied the same ideas. Characterization of A2 as an affine manifold. So the result is like this. If you take S smooth affine complex surface, then S is algebraically isomorphic to A2 if and only if, well, the pi1 at infinity of S viewed as a complex analytic space is trivial. The result is usually written as S has to be topologically contractible and simply connected at infinity, but actually you just need to assume this. And the proof basically goes like Mumford's argument. So you take, no, instead of taking log resolution, you take some SNC compactification. Right? So this one says a smooth projective surface. And the boundary, let's call it DS, is an SNC divisor. Then, well, you can get pi1 infinity of S as the pi1 of a good tubular neighborhood of delta S in S bar minus S. And then what Ramanujam is doing is using the presentation constructed by Mumford's plumbing. And from this hypothesis that pi1 at infinity of S is 1, you can pretty much conclude in the same way that this delta S is a tree of P1. And now there is a big difference. This delta S is what happens at infinity of a completion of an affine surface. So certainly the intersection matrix here cannot be negative definite. This guy is the support of an ample divisor because the complement is affine in that case. So, but what Ramanujam argued, and this is much more difficult actually, is that this implies that there exists that, well, this implies that after finitely many contractions of P1s with normal bundles OP1 of -1 intersecting at most two other components of delta S, you get a new completion S bar prime delta S prime, where delta S prime is a P1, with normal bundle. OP1 of 1. So that's the main difference. You know, just some standard theory of open surface tells you that, in fact, you immediately get that S bar prime, this pair, cannot be anything else than P2 on the line. This is a line. So from which you get that S is P2 minus P1, which is A2. So this is genuinely a use of the topological notion of fundamental group at infinity and Mumford's plumbing computation to get a presentation in that case, which yield this algebraic characterization of A2 just by a property about its topological fundamental group at infinity. So, okay, now, as you imagine, Jam is to try to import this in A1-homotopy. And well, how can you do that? The main problem is that you start with something which is the n space, so a set of maps. And there is no immediate proper maps. Obvious analog of this, you could imagine walking on the A1-homotopy category of smooth scheme over a field set. But you can observe something is that this n space is related to the one-point compactification. One-point compactification. So M infinity is just M with a disjoint point and the topology so that it becomes a manifold. And then I told you there is a natural map from the M space of M to M. And on the other end, you can just plug infinity here and take the obvious map to M infinity. So here you just embed M as an open subset of M infinity, and this is just the inclusion of the point at infinity into M infinity. And the topological observation is that this is a homotopy fiber sequence. So this you have a chance to import. Now, if you take X, K, separated, K scheme of phi type, then you can find some open immersion into complete or proper K scheme with some boundary dx. So, okay, that's some kind of one-point compactification, but depending on a choice. And now you can just reproduce exactly this sequence and try to declare that. So here you have both inclusion inside bar, and you would like some object here, which would be the n space of X, just defined as this homotopy fiber here, right? Homotopy fiber. But where? So so the simplest thing you could imagine probably is to work in the unstable A1-homotopy category. But you stabilize by inverting simplicial suspension. And then you could really define this E of X as S minus 1, the homotopy cofiber of this. And this would make sense, actually. And but of course, this defined this way, this really depends on your chosen compactification at the beginning. So you would want to make it independent. Make it independent. On the choice. Of the initial embedding. So that's something many people thought about. Rav in Asok, we had discussion with Polarner about this. One way, if we work in the unstable A1-homotopy category, would be to take the limit over all possible compactification, knowing that whenever you have two compactification, they are dominated by a third one. But now, if you work instead, work in the stable. Then there, you basically have CDH descent, so it will be by design independent on the choice of this compactification. So you have a well-defined, get a well-defined object, which is independent on the choice of a compactification. And well, what you get then from the definition, if you let's call it this get something which for x is called pi infinity of x, which would be the stable A1-homotopy type. Pi at infinity of x. So it's quite unpleasant to use choices to define something and argue that after all it is independent on the choices made. But it turns out a much more satisfactory definition was found by Frederick, inspired from topological consideration. And let me explain you this by reconstructing it totally the other way. So, so we had by construction this exact sequence. X goes to X bar, and here we have this homotopy cofiber. Which we want to be basically pi infinity of x shifted by 1. But if you rewrite this, you can just view this sequence as the same thing as that one. And now just complete the diagram with obvious things. So here, this is the natural inclusion. And then this is the inclusion. This is and this is X. And if you look at this bottom row, basically this guy will correspond to the usual homotopy type of X, stable homotopy type of X. While this guy is the properly supported stable homotopy type. Homotopy type of X. And so this means that this bottom row can be defined independently on the choice of the compactification. If you look topologically, this would correspond to looking at the singular chain complex of Xn, say, chain complex. This goes into what will compute the Borel-Moore homology of X. So this is the chain complex of locally finite singular chains. And then here you have the quotient, which is, well, let's call it S plus 1, the infinity of X. So this bottom row reproduce the formally the complex that topologists are using to express the homology type at infinity as fitting into a sequence using the homology groups and the Borel-Moore homology group of X. It should be everywhere. Okay, so now we can just, with this basic definition, mimic a couple of computations we did for topological manifolds, for example, just to test whether it works well or not. So take X is the affine space AD, and take for X bar its projective space of dimension D. And then delta X is just what? PD minus 1, and with normal bundle OPD minus 1 and 1. And if you unwind everything upstairs, you will find that this pi infinity of X is just the homotopy fiber of the map from delta X to the Thom space of the normal bundle of delta X in that case, given by the zero section. So we have this homotopy sequence. And so this just tells you in that case, exactly like in the topological case, that this is basically the normal bundle of delta X minus the zero section, just by definition of the Thom space, basically. Okay, good. And this we know how to compute because OPD minus 1 of 1 minus the zero section. This is just AD minus 0, which is even in the unstable homotopy category. Well, let's say this is S minus 1, which P1 slash D. So this just has the homotopy type of the expected sphere of dimension 1 less, say, right? Conclusion is the homotopy type of AD minus 0. The usual homotopy type. And more the thing we just did apply more generally whenever you take a projective variety and remove smooth hypersurface, exactly like in the topological setting. Now, in general, what we want to do is motivic Mumford plumbing. So the situation is the following: you have x bar, some compactification, assume x is smooth, compactification with a SNC boundary. Dx. So this dx is a union of irreducible component dix. And well, from the topological consideration and the previous example, we know that if dx is just one di of x, then the pi infinity of x is just the normal space of di of x minus the zero section. So exactly as in Mumford consideration, we would like to build our knowledge of let me be clear. So we have on the other end this homotopy sequence, what x bar x and by infinity of x shifted by 1. So we want to compute the homotopy fiber or the homotopy cofiber of this map. And we know how to do it in the case where delta x is just one component. So we have to find one way of patching information for each component to get an explicit description of this map. And this is what we develop in the paper with Frederick and Polarner. I can just give you the result and finish with this. So the theorem is as follows. So you take this, all these hypotheses, the components are like that. So first you have to compute this guy, but this guy, you can express it in a natural way. Here you take all the di, then you take pairwise intersection, dijx, I strictly smaller than j, and you continue. And the first observation, this is an homotopy exact sequence. So you can just compute this delta x as this in terms of this diagram. And then so that's the first ingredient. Then the other ingredient is that if you want to compute this, this will, well, maybe let me hide something. what you can consider on the other hand are homotopy type twisted by vector bundles. So you take dix twisted by their normal bundle. Then you can go to the dijx twisted by normal bundle of intersection and get a complex like that. And let me say that this basically compute this guy. No, that's a very vague and wrong statement. Don't like that. But okay, the whole point is that if you just insert this map here, which is the only one you can imagine. You take an irreducible component of this boundary, and here you intersect it with another irreducible component. This is induced by the intersection of divisors on this surface. Then if I with an eraser, yeah, if I just, whoops, sorry, never mind. So if I get rid of this, get rid of that, if I look at this long sequence, then this is really Mumford plumbing. It expresses you what is the homotopy type of this punctured tubular neighborhood of delta x by infinity of x, which is by definition pi of tubular neighborhood of delta x minus x, whatever it means, is the homotopy fiber of the diagram. Is the homotopy fiber of the diagram of the above of the diagram. Okay, that's very, very vague, but just to give you an idea that what Mumford did topologically by describing gluings between circle bundles of a components can be expressed in terms of this diagram. So it's really some motivic Mumford plumbing construction, and as a reward, you get this expression of this pi1 at infinity. Of course, the question is to compute the homotopy fiber of this guy, but in some circumstances, this is really doable, especially if you work with, as in the Mumford situation, you work with surfaces that you assume that the delta I are just copies of P1. So this part is basically uniquely encoded by the dual graph of the configuration of P1, and this part is dual. And here you have to understand the motivic version of the self-intersection matrix of your graph of P1. And, in certain circumstances, this is doable. And if you want to see some explicit computation, which I won't have time to do, you can have a look at the paper. Okay, sorry for being over time. Thank you for your attention.
Okay, great. Let's thank Adrien for a really nice talk. Hey, are there any questions?
So the tubular neighborhood of delta x is a smooth minus delta x is a smooth analytically. Is there any way to see the homotopy type you get as the homotopy type of a smooth scheme or something close to it? As in, could you have a tangent bundle on it, etc.?
Well, just think about any P1 And then you can take any line bundle you wish in it. So what you will have in that case is the homotopy type of of a GM bundle. And more generally, I guess, I mean, well, I mean, this is
but it's cool in the
homotopy type
case
in
of
itself.
the.
It's not expressible by simpler objects in general.
Well, there are tools like surgery theory to decide whether a homotopy type has the homotopy type of a manifold. So I liked your picture with these crossing axes, and then you have the smooth tubular sphere bundle.
Yes.
So the crossing axis singular. You've got the smooth sphere bundle smooth, and then you could hope for an analog of the data that goes from homotopy type to smooth thing, and show that this homotopy type, hey, it looks more smooth because it comes from this kind of plumbing game. And I mean, the start of that story is you get like a tangent bundle that will be like a tangent bundle, and then surgery, etc. Surgery instruction, something or another.
Yeah. I have no idea for the moment whether we can find such kind of comparison at the modific level. I mean, what Mumford is really doing is constructing an object, a smooth geometric object, which has the homotopy type of this punctured neighborhood. But I mean, that's a gluing with some smoothings, and it's just a differential stuff. So I don't know whether we could find some nice scheme representative of these homotopy types in general. That's a good question.
I have a quick question. If you can you show your last screen again?
Oh yes. Let me up.
So yeah, so I think you should have in this bottom thing where you have the first. I think there should be two arrows going out of the delta IX to the delta IJ X.
Oh, you mean the only one vertical arrow?
No, not the vertical arrow. When you go vertical and then take a left turn, going from the delta
Wow,
X,
there is a direct sum here.
No. Yeah, but the next arrow to the right, shouldn't that be two arrows?
Yes, there are two. Yeah,
that's what I meant.
It's just
yeah. So here's, you want to make a complex out of this, and somehow you need to know that the funny composition should be 0.
Yes.
So isn't that a problem? It's sort of a self-intersection problem. And it's sort of we have 0 up to homotopy, but then you have to make a complex. You have to explicitly make the homotopy. So
in general, if you want to unwind this to get something usable, there is a lot of work. I agree.
I mean, just to define an object, though. So you're patching together, those are complexes. You want to get something which is a complex, but you're working in some...
No, wait.
Yeah, see, what I mean is, like, you have these delta IJXs going into the delta IX, and then you're going back. Yeah, and that's just the inclusion, but then you're going back, you're intersecting again with the delta IJX NIJ.
Yes.
So it's sort of a self-intersection.
It is.
And you need certain things to cancel out in order to get a well-defined object.
That's a good point, yes.
I think, maybe. I mean, I remember some problem like this coming up before somewhere. But maybe I'm misunderstanding that. So, I mean, are you kind of canceling out what you're getting rid of? You're getting rid of something when you put this thing together, or are all the terms there, or this? Oh, maybe all the terms are there. So maybe it's not a problem. Okay, so I think I misunderstood something. And I just want to mention there is some really horrible construction that I made, which does give some kind of funny punctured tubular neighborhood, which is it's an awful construction. I wouldn't recommend it to anyone. But it does.
I think we started with this when we first discussed with Polano about a possible unstable version of this consideration to use your punctured tubular neighborhood construction. But then there are some you want to take limits over all possible
no, it's a horrible
completion, and you don't know if you want to do first tubular neighborhood, then limits on completion, or the opposite.
But it just reminded me a little bit about this 0 to infinity construction, where you can make like this punctured disk construction using that construction. Yeah. Right. And that might be something. You look at maps of that. That's just one object, and you might be able to define your space at infinity by taking a space of maps of that object. No. You need to say something that the limit point is not going into your, so you have the punctured disk, and that goes inside the whole disk. Yeah. So you'd want to sort of take maps of the punctured disk that don't extend to maps of the whole disk. Yeah, proper maps. It's not really proper, but something like locally proper at infinity or something. Yeah, exactly. So I mean, that's the object is there. It's probably it's less confusing than my construction because you just have this one object. Yeah. It's this sort of local, right? It's this local neighborhoods of the fiber, the delta n over the point inside the delta n of the neighborhood. But yeah, I mean, it just reminded me of that a little bit. No, it's more definitely related. Yeah. Sorry, it's not a question. I was just no, but it's making good to. Okay, that was all. Thanks.
I have a much more naive question. In the old days, there used to be two approaches to singularities, for say singularities of curves. There was the embedding them in a smooth family, which is basically what the plumbing construction does. And then there was the notion of gluing, where you would just take 2 points, for example, on a curve and identify them. Do you have any way of thinking about that second approach in your context? In other words, gluing two varieties together.
Yeah, well, by this kind of you identify some close equivalence relation, that kind of stuff you would want to extend from curves to arbitrary schemes.
I mean, for example, consider a node on an elliptic surface. Yeah. Take 2 points on an elliptic curve and glue them together. Yeah. And you get a surface with this 1 point singularity. Yes. So then you can look locally at the plumbing, or you can sort of think about detaching the thing. Okay, so some kind of local normalization which separates branches. Yeah. Yes. I don't know. I have no idea whether we can do this kind of gluing actually. Yeah, maybe it makes sense in the homotopy category, even though it does not make sense with schemes directly. Okay, that's. I don't know. That's a good remark. Yeah. Okay, thanks.
Okay, well, thanks for the suggestion.
Any other questions or comments?
Can you hear me?
Yes.
Adrien, can you? So sorry, my mic was kind of was cut. So Adrien, can you? I want to maybe add some clarification to answer Mark's question. Can you show again the diagram, Adrien?
Yes. Just give me a second.
Okay. So the picture tells you that if you look at the bottom line, you have a semi-simplicial object in the say, stable infinity category, SH of K, and which compute the stable homotopy type of partial X. And below you have a dual object, which is a co-semi-simplicial object, which computes this X bar X, these relative things. And so you have a map between a homotopy co-limit and a homotopy limit, which is given by this auto-intersection, so to speak, this map, the vertical map. And the assertion is that pi infinity is the homotopy co-fiber of that letter map.
Fiber.
So
Fiber.
homotopy fiber, sorry. Yeah.
Yeah.
So it's a picture to view the situation. You can probably, by using, I think that by using infinity way, you can probably say that this diagram is a homotopy coherent diagram, and I would hope that pi infinity is the homotopy co-limit of this diagram, but I'm yeah, not completely sure. But it looks like gluing two complexes. That's
yes,
right.
yes, that's true.
Absolutely. But
the
I
glue
guess
the glue has to be sticky enough for it to glue together.
Yeah, maybe by using infinity co-limit. I did not try to make it clear, but
so what is
might
this?
be.
Maybe I'm a little confused. What exactly is this object delta nx comma n? Delta.
It's just the term space of ni, and ni is the normal bundle of partial ix to the compactification. So
Yeah.
actually, it's just the term space, if you want.
In that case, yeah.
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 Yeah, if you think about the smooth case, it's just the zero section, the vertical map is just the zero section, is just induced by the zero section of the normal bound.
But you need something to say that the sum of the delta ijx's, when you go into the sum of the delta ix's and then go into the sum of the delta ixni's, that it lands in the homotopy fiber of the next map in order to get a gluing. You can't just, right? You can't just, you need the top thing has relations, and you need to know the relations are satisfied when you pass from the simplicial thing to the co-simplicial thing.
You mean from the above to bottom?
Yes.
Or?
I mean, you need to know, I mean, the simplicial thing is sort of like a quotient, right?
Yeah.
A limit. And so you need to know that the relations represented by the sum of the delta ix's, when they map into the sum of the delta ix comma ni's, it has to canonically factor through the homotopy fiber of the next two maps going to the right.
I think so, but it's just given by the computation. Actually, we compute, say, the infinite suspension of this partial x, which is singular, but it has this kind of CDH resolution, which, and then we also compute the other term, and we just have a map between these two things, and then we have a map between the two diagrams. So.
Oh, okay. So you just,
it seems,
it comes from the fact that by the definition, you start with a map from dx to x bar mod x.
Ah, okay.
So this one, this is a resolution of dx, and this is a resolution
that
of
gives you the map. But then I guess the issue becomes, if you want to use this description to compute anything,
yes,
you have to use the fact that it comes from a map. Then you have to unwind it to see where these homotopies are going. You know that there's a map in an abstract sense.
Yeah.
But you don't know exactly.
Yeah, we had this abstract map from dx to x bar mod x.
Yeah.
And now it's expressed only in terms of the components of dx and their normal bundles and some intersection theoretic properties. And this you have a chance to compute more effectively.
Right. But I think, I guess what I'm trying to say is that when you start to make explicit computations, these higher homotopies needed to realize the obvious map as a map of these complexes start to come into play. Possible, but maybe I'm wrong. I don't know. Okay, that's all. Now I'm
So we did computations for the case of pi1 or surfaces and pi1.
Yeah, projective lines on surfaces is doable with this because the complex are short.
Yeah, okay, that's interesting.
And we know what is the self-intersection of a P1 or the intersection of two P1 on a surface, just counting points appropriately. So.
Yeah, maybe a little teaser. We define a quadratic Mumford matrix. So that is a Mumford matrix, but with coefficient in quadratic in GW of the base field in certain circumstances.
Yeah, nice.
Yeah, which is the way you can compute this vertical map explicitly in certain cases, just as matrix with coefficient in GW of K. If you work with P1s and under suitable assumptions.
Okay, great. And any other questions? I think that's all for today then. And let's thank Adrien again for his really nice talk.
Thank you.